Figure 4 shows a Geiger-Müller tube, a GM tube used for measuring radioactivity. Describe how a teacher should use a Geiger-Müller tube to compare the count rates from two different radioactive rocks. So describe means just say what you'll do. You don't have to give a reason for why you're doing it. So basically, you want to place your rock samples near the mouth of the Geiger-Müller tube. And what you want to make sure, obviously, is that you place each rock at the same distance, because you don't want, if you obviously put one rock further back, it might receive less radiation or the count might be low. It might affect the count. So to keep it fair, you need to put both rocks at the same distance from the mouth of the GM tube, and you take the reading. What you might also want to take into account is all this time you're getting radiation from which naturally occurs from surrounding materials like rocks and the environment, which is called background radiation. And it will be picked up by the GM tube as well. So you'd want to account for that by subtracting the amount, the level of background radiation. And you simply do that by removing those, taking a reading of the background radiation, and then subtracting that value from the reading of the rocks. You might actually want to take multiple readings in multiple directions to make sure you get an accurate average of background radiation. So that's pretty simple. So how do we express that? Well, we say put rocks in front of tube. Very easy. Then we say measure the count rate for each rock separately. Obviously, we want to do it at the same time for the same amount of time, because otherwise, if one has a longer exposure to the GM tube, or if the GM tube has a longer exposure to one of the rocks, the count will be higher, and at the same distance from the tube. You can take background radiation into account, and if you say that, you get a mark as well. So there's a number of ways of getting different marks. So notice this, it's just how you're going to measure it fairly, and what will you control to make sure it is measured fairly. All good experiments involve control. So here we're controlling time and distance. A hospital uses a radioactive isotope with a half-life of 6 hours. That means every 6 hours, its radioactivity count decreases by half. So if it's 100, 6 hours later, it'll have a count of 50. 6 hours later, it'll have a count of 25, and so on. A technician measures a count rate of 80 counts per minute from this isotope. That's just a radioactive material in this context. Complete the graph on figure 5 as accurately as possible to show how the count rate from this isotope will change from the time of the first measurement. The first point is already drawn. So I've drawn an X here. So every 6 hours you're looking for a reduction by half in that count. You'd actually just get a mark. This is for 3 marks, easy 3 marks. You just get actually just doing this curve shape will get you a mark. Always remember that a decay curve for half-life, a decay curve for a radioactive isotope always has this shape here. So if you just draw that curve shape, you will always get a mark when in doubt. But you should be able to do this anyway. So if you look here, the first thing I would do is I'd mark 6 hours along the bottom. So make sure you get the scale correctly here. And the scale is every 2 is equal to 1 hour. Every 2 small squares is 1 hour. So 6 would be here, 12 would be here, and 18 there. Do that first. Then go up here and go to half the value. So 6 hours are gone. This will have dropped by half. So 40 will occur at 6 hours. Then this will drop by half to 20. That will be at 12 hours. Drop to 10. And that will be at 18 hours. One radioactive source is used in hospitals is technetium. Technetium is produced from the radioactive decay of molybdenum, MO. Complete the following nuclear equation. So basically, you've got to know that if you look here, it says beta. So you know it's decaying via beta radiation, not alpha, and it would never say gamma here. So let's just look at the 2 types of radioactive decay. With alpha, what you've got here is a helium nucleus. So when the nucleus decays, so radioactive decay is just when the nucleus ejects matter. When it decays via alpha radiation, you lose 2 protons and 2 neutrons. This is called a helium nucleus because the nucleus of a helium atom is this. Now this has 2 effects on the nucleus. The first one is the atomic number, the number of protons for the element, will drop by 2 because you're losing 2 protons. And the atomic mass, which is accounted for by the number of neutrons and protons, will drop by 4 because you're losing 2 protons and 2 neutrons. So if this was decaying by alpha radiation, which it's not, it says beta, this would drop by 4, the mass at the top would drop by 4, and the atomic number would drop by 2. So this would become 95 and this would become 40. However, what's happening here instead is we're having beta decay. Now, a beta decay, what happens is a nucleus, not a nucleus, a neutron will become a proton. It's converted to a proton, and an electron is basically shot out. So a high-speed electron is released. You can think a little bit that a neutron, what it is, the reason it's a neutral charge is because it's a proton and an electron together, and because of that there's no overall charge, and what's happening is the electron is firing off and there's a proton left behind, so the neutron status is changed. Anyway, so what we're saying here is that if you think about it, there's no change in mass because a neutron and a proton have the same mass. An electron has next to no mass. So there's no change in mass because we're just substituting like for like, but there is an increase in the number of protons. So the atomic number for beta decay will go up by 1, whereas alpha, remember, it goes down by 2. And I'm teaching about alpha because next time it could be a question about alpha. But the atomic mass stays the same because we haven't actually lost any particles that have significant mass. We've just substituted one particle for another, so the mass stays the same but the atomic number increases. So what we have to write here is we write 99 for the atomic mass because it stays the same, and 43 for the atomic number because it's increased in number of protons.